So, before we dive into the spectroscopy of berberine, we need to know the identity of berberine itself. So, it has the IUPAC name, which is 9,10-dimethoxy 5,6-dihydro 1,3-dioxolo for 5G isoquinolino 3,2A isoquinoline 7-EU, and it has the molecular weight, which is 336.36 gram per mole. And also, for the molecular formula itself is C20H18NO4. That's all for the identity. Next, we move into the spectroscopy of berberine.
Assalamualaikum and hello everyone. Today I will explain how FTIR is used to identify functional groups in berberine. Before we analyze the spectrum, I'd like to ask a question. Have you ever wondered how chemists can identify a compound without actually seeing a molecules? One of the techniques we use is Fourier transform infrared spectroscopy, or we call it as FTIR. FTIR works because every chemical bond is constantly vibrating. When infrared light is passed through a sample, only those bonds whose vibration matches the energy of the infrared light will absorb it. Think of it like pushing someone on a swing. If you push at the right rhythm, the swing moves higher. Similarly, when the infrared frequency matches the natural vibration of a chemical bond, the bond absorbs the energy. This absorption produces an absorption band, and every functional group absorbs at a characteristic wave number. That is why we call FTIR is a fingerprint technique. Before we analyze the spectrum, whenever you analyze the FTIR spectrum, we don't immediately guess the functional group. Instead, we ask 4 questions. First, where is this absorption band located? This will tell us the possible functional group because each bond absorbs within a specific wave number range. Second, is the band broad or sharp? Broad bands usually indicate hydrogen bond, while sharp bands represent more uniform bond vibration. Third, how intense is the band? The intensity tells us how strongly the bond absorbs infrared radiation. Finally, does the absorption match the molecular structure of our compound? Now we look at the first major peak appears at 3128 per centimeter. This is assigned to OH stretching and it appears broad. Why is it broad? Broad OH peaks are caused by hydrogen bonding. Hydrogen bonding causes slightly different bond strengths among molecules. So the OH bonds vibrate over a range of frequencies instead of one exact frequency. Therefore, instead of sharp peak, we observe a broad band. Although berberine itself does not contain a free hydroxyl group, this broad absorption is generally attributed to hydrogen-bonded moisture or solvent molecules associated with the sample. Next is the peak at 3022 per centimeter. This corresponds to aromatic CH stretching and has medium intensity. The intensity is medium because aromatic CH bonds have a moderate change in a dipole moment during vibration. They absorb infrared radiation but not as strongly as highly polar bonds. This peak confirms the presence of aromatic rings in berberine. The peak at 2832 per centimeter is assigned to methoxy stretching. Its intensity is weak. This is because CH bonds are only slightly polar. Since the change in dipole moment during vibration is relatively small, they absorb infrared radiation weakly. This peak confirms the presence of methoxy groups attached to the aromatic ring. So next, at 1631 per centimeter, we observe iminium C++ plus stretching. The vibration is characteristic of the positively charged nitrogen atom present in berberine. The peak has medium intensity, indicating a moderate dipole change during vibration. Now, at peak 1599 per centimeter, peak corresponds to aromatic C++C stretching. This confirms the conjugated aromatic system in berberine. Conjugation causes electrons to become delocalized across the aromatic rings, slightly lowering the vibration frequency compared with isolated double bond. The peak at 1504 per centimeter represents the skeletal vibration of the aromatic ring. It has a weak intensity because the vibration produces only a small change in dipole moment. So, it provides additional evidence for the aromatic structure. Most intense peak appears at 1403 per centimeter. This is assigned to symmetric and asymmetric CH bending. It is classified as strong because this vibration causes a relatively large change in dipole moment, allowing efficient absorption of infrared radiation. This is one of the characteristic peaks of berberine. The 1366 per centimeter peak corresponds to method C CH bending. The medium intensity reflects a moderate dipole moment change during a bending vibration. The 1273 per centimeter peak is assigned to CO stretching in the method C or aryl ether groups. Since the CO bond is more polar than a CH bond, it absorbs infrared radiation more effectively, producing a medium intensity peak. The 1105 per centimeter peak corresponds to COC stretching. This confirms the presence of ether linkages formed by the method C groups. The 1036 per centimeter peak is assigned to ether CO stretching. Although weaker than the previous peak, it further supports the existence of ether functional groups in berberine. Lastly, the 775 per centimeter peak represents aromatic CH out of plane bending. The vibration is characteristic of substituted aromatic rings and provided further confirmation of berberine's aromatic framework.
Okay guys, now let's move on to 1H&MR spectrum. So what is it, H&MR spectrum? So I will explain to you guys first. So H&MR or proton nuclear magnetic resonance is a technique used to analyze the different hydrogen environments in a molecule. It works by detecting how non-hydrogen nuclei respond to a magnetic field, and the signal produced give information about their chemical environment. So for our compound, which is berberine, the molecular structure contains 18 hydrogen atoms that contribute to the 1H&MR spectrum. So these protons are present in different environments such as aromatic, method C, and also aliphatic regions. So this results in different signals in the spectrum. So in this spectrum, the chemical shift range is from 0 to 10 ppm. Signals appearing on the left side of the spectrum have higher chemical shift and are considered more downfield, meaning the protons are more de-sheltered. Meanwhile, signals appearing on the right side of the spectrum have lower chemical shift and are more upfield, meaning the protons are more shielded. Therefore, by analyzing the chemical shift, integration ratio, and also splitting pattern of the signal, we can identify and assign the corresponding protons in the berberine structure. Now, I will explain each signal peak in detail. Now, let's have a look of peak 1. So, starting with the most downfield signal, the first peak appears at 9.58 ppm, which is assigned to hydrogen 32. So, this signal has an integration ratio of 1 hydrogen, meaning it represents 1 proton. So, since this peak appears far to the left side of the spectrum, hydrogen 32 is considered highly de-sheltered. This proton is located in the heteroaromatic region of berberine. So, the de-shielding effect can be explained by the isoquinoline system, where the nitrogen atom carries a positive charge. The positively charged nitrogen withdraws electron density from the ring system, causing nearby protons to experience less shielding and appear at a higher chemical shift. The signal appears as a triplet, suggesting that hydrogen 32 is coupled with 2 neighboring equivalent protons. We move on to peak 2. So, the next signal appears at 8.44 ppm, and which is assigned to hydrogen 30. So, this signal has a ratio of 1 and appears as a multiplet. The position of this peak places it within the aromatic region. It appears relatively downfield because the proton is affected by the conjugated aromatic system and the electron withdrawing effect from the nitrogen containing ring. So, the multiplet pattern suggests that hydrogen 30 experiences coupling with several neighboring non-equivalent aromatic protons. Next, for peak 3, At 6.94 ppm, the signal is assigned to hydrogen 29 with a ratio of 1 hydrogen. So this peak is also located in the aromatic region. So compared to the previous signals, it appears slightly more upfield, meaning the proton experiences a greater shielding effect. The signal appears as a multiplet, which comes from coupling interaction with neighboring aromatic proton. Next, we look at peak 4. So, the signal appears at 6.71 ppm, correspond to hydrogen 40. So, this proton appears in the aromatic region with an integration ratio of 1 hydrogen. So, the signal appears as a doublet, showing that hydrogen 40 is coupled with one neighboring proton, causing the signal to split into two peaks. Next, for peak 5, the signal appears at 6.51 ppm, which is assigned to hydrogen 41 with a ratio of 1 hydrogen. So this proton appears as a triplet in the aromatic region. The triplet pattern suggests coupling with two neighboring equivalent protons following the n+1 splitting rule. Next, for peak 6, another signal appears at 6.51 ppm, which is assigned to hydrogen 31. So, although it appears at the same chemical shift as hydrogen 41 just now, the splitting pattern is different, where hydrogen 31 appears as a multiplet. So, this suggests that hydrogen 31 is in a similar chemical environment but experiences different coupling interactions with surrounding protons. Okay, for peak 7, moving towards the right side of the spectrum, the signal at 3.81 ppm appears in the more upfield region. This peak has an integration ratio of 6 hydrogen and which is assigned to hydrogen 26, 27, 28, 33, 34 and also 35. So, the signal appears as a singlet, which means there is no significant coupling with neighboring proton. So, this peak corresponds to two metal C group, which is OCH3, and each metal C group contributes 3 equivalent protons, giving a total of 6 protons. So, because of these protons have similar chemical environment, their signals overlap and appear as one singlet. So, for peak 8 at 3.74 ppm, this signal is assigned to hydrogen 42 and hydrogen 43 with an integration of ratio is to hydrogen. So, these protons correspond to a methylene group, which is CH2. So, the chemical shift in this region suggests that the methylene group is located near an electronegative atom, which causes slight deshielding. So, the signal appears as a singlet, indicating minimal coupling with neighboring proton. Okay, for peak 9, another signal at 3.74 ppm, which is assigned to the hydrogen 37 with a ratio of 1 hydrogen. So, although it appears at the same chemical shift as hydrogen 42 and 43 just now, it represents a different proton environment. So, the signal appears as a multiplet, suggesting more complex coupling interactions with nearby proton. And then, for peak 10, the signal at 3.50 ppm corresponds to hydrogen 36 with a ratio of 1 hydrogen. This peak appears further upfield, showing that this proton is more shielded. The multiplet pattern comes from interaction with neighboring proton in its aliphatic environments. And for the last peak, which is 11 peak, the signal appears at 2.17 ppm, which is assigned to hydrogen 38 and 39 with an integration of hydrogen is 2. So, these protons also correspond to a methylene group, which is CH2. Since the signal appears further upfield, it suggests that these protons are more shielded and are located in a less electron withdrawing environment. So, the multiplet pattern arises from coupling with nearby protons.
So, we move to the carbon NMR of berberine, which it contains 14 non-equivalent of carbon and 6 symmetry, that resulting in one signal peak of carbon 16 and 17, carbon 9 and 90, carbon 18 and 15. So, this is a key characteristic of benzodiazole and isoquinolinium in this structure. Moving to the most downfield region in this spectrum, we can find the peak of carbon 14 at 157.10 ppm. this is the most shaded carbon, and its specific position between isoquinolinium and benzene rings can generate an electronic pull and shifting its absorption further downfield than any other carbon. Next, we can see three distinct signals in 151 to 152 ppm range. First, carbon 10 appears at 152.04 ppm due to its methyl-C attachment at the central ring system. Then, at 151.90 ppm, we can see asymmetric signals that produce one peak that represents both carbon 16 and carbon 17 from benzodiazol ring. And finally, carbon 7 absorbs at 151.70 ppm with the adjacent of quaternary nitrogen. Peak at carbon 8, which is 151.06 ppm, is slightly different than carbon 7 because it sits within a single aromatic ring. We also can observe carbon 2 at 149.17 ppm, although it has a methyl-C attachment like carbon 10, but it is more shielded because it is further from the isoquinolinium's strong resonance effects. From this comparison, we can know this carbon has a similar attachment but different chemical shift value. Now, we look at the signal peak of carbon 5, which absorbs at the 144.88 ppm. This carbon serves as a bridge and position between an adjacent benzene ring and the isoquinolinium ring system that contains the quaternary nitrogen. Next, we can see another three distinct signal peak in the range of 129 to 132 ppm range. First, at 132.04 ppm, that represents both carbon 9 and carbon 19, which are quaternary bridgehead carbons that sharing identical environment. We also can see an aromatic carbon 4 at 131.13 ppm. And lastly, the third signal at 129.31 ppm corresponds to the aromatic methynes of carbon 15 and carbon 18 that attach on opposite sides of benzodiazole ring. Moreover, carbon 3 absorbs at 111.82 ppm with its shift influenced by ortho position to a methyl-C group. Then, carbon 6 at 105.26 ppm is distinguished by earlier signals like carbon 8 because it lacks a direct bond to the nitrogen atom. And lastly, a peak appears at 98.82 ppm for carbon 20 because this is the methylene dioxide bridge carbon and its attachment with two electronegative oxygens that place it in this distinct region. Next, we move to the methyl-C region. In this region, we can find two signals that are very close together. First, carbon 1 at 60.70 ppm and second, carbon 11 at 59.99 ppm. While they belong to the same functional group, the delocalization within benzene ring creates the differences in their electronic environments. This allows us to resolve them as two separate peaks. Then, chemical shift for carbon 12 appears at 49.05 ppm as methylene carbon that directly bonded to the quaternary nitrogen. It is shifted significantly compared to the standard alkanes. Lastly, we can find the peak of carbon 13 at 30.68 ppm. This is the most shaded carbon in the berberine molecule that appears as atypical in aliphatic methylene region, far from the shielding effect. That's all from the NMR spectroscopy of berberine. Thank you. Now, let's learn about the mass spectroscopy of berberine. First, let's take a look at this MS spectrum data. It shows the molecular ion of berberine at mass to charge ratio 336.1251. As we fragment these ions, we can see a variety of product ions, and the most significant one is base P, which is mass to charge ratio at 320.0930. It indicates the most stable fragment that can be formed during this process. how can we do the fermentation? So this diagram shows the first step. How can we produce the molecular ion of berberine, which is ionization. In this ionization step of fermentation, we can see a neutral berberine molecule is hit by an electron beam. This high energy impact knocks out an electron, ionizing the molecule and creating the radical cation. As we can see here, a product of berberine with a mass to charge ratio of 336.1251. After the ionization step, this is the second step, which is fragmentation pathway. So based on this diagram, this is the first pathway, that loss of the two methyl radicals. The first fragmentation pathway involves the loss of two methyl radicals from the methoxy groups. This specific cleavage is favorable because it produces a resonance stabilized aromatic ion and appearing in our spectrum at mass to charge ratio 306.0778. Next, we move to the second fermentation pathway of berberine, which is elimination of methane. Second fermentation pathway is elimination of methane. By removing a methyl group and an adjacent hydrogen, the resulting positive charge can be deliqualized throughout the aromatic system. This high degree stability is why the ion at mass to charge ratio 320.0930 forms berberine-based peak. And lastly, this is the third possible of fermentation pathway of berberine, which is the elimination of one methoxy group. Lastly, the third fermentation pathway of berberine is the loss of one methoxy group. Similar to the previous steps, the cleavage of this group from the aromatic ring can generate a positive charge that can be stabilized through delocalization in the conjugated ring system, resulting the fragment ion at mass to charge ratio 304.0968. That's all for the mass spectroscopy of berberine. Thank you.
Let's begin by analyzing the UVB spectrum of the berberine compound. Our main focus on this slide is the absorption peak at 2030 nm. This represents a high energy absorption that is highly specific to the berberine molecular structure, attributed to the presence of aromatic double bonds within the benzene ring. To understand why this peak occurs, we look at this energy level diagram. The area in red represents the pi to pi star transition. This occurs because berberine contains conjugated double bond, which is C double bond to C, that have electron occupying pi bonding orbitals. When the molecule absorbs energy, these electrons jump to the pi star antibonding orbital. Because there is a large energy gap here, it requires high energy lag, which create the prominent peak that we observe at 230 nm. So, to conclude, the presence of the peak at 230 nm provide crucial evidence regarding the chemical structure of berberine. It's confirmed the existence of the conjugated aromatic system within the molecule. So, overall, this spectroscopic data is highly consistent with the structural profile of the berberine that we are studying. Next, we look at the absorption peak at 266 nm. This peak is particularly interesting because it involves the methoxy group, which is OCH3, which acts as an auxochrome. So, by having lone pair electrons at O, this auxochrome attached to the conjugated aromatic system and increase pi electron delocalization, which influence the electron transition that we observe. So, if we refer back to the energy diagram, this peak also represents a pi to pi star electronic transition, just as with our previous peak. To summarize, the 266 nm peak confirmed the role of the conjugated aromatic pi system in berberine. The lone pair electrons on the oxygen atom of the methoxy group further extend the delocalization of pi electrons. So, this enhanced delocalization is key to the understanding the specific optical properties of the berberine molecule. Next, moving to the 350 nm peak, we are now looking at the protoberberine or isoquinolinium ring system. This peak indicates a different type of electronic environment compared to the previous one. So, the absorption here is associated with highly delocalized pi electron, which significantly lower the excitation energy that required for the transition. Okay, the electronic transition observed at 350 nm is still pi to pi star transition, which is same as previous. In summary, this peak highlight the importance of electron delocalization in the protoberberine structure. Then, nitrogen atom within the ring, which act as an electronic center that extend the conjugated system, increasing pi electron delocalization and lowering the energy required for excitation. Because the pi electrons are highly delocalized, the molecule requires less energy to be excited. This confirms that the more extensive the conjugated system, the lower the energy. Finally, we reach the absorption peak at 425 nm. As you can see, this is a weak absorption peak with a much lower intensity compared to the earlier transition. Then, this peak is associated with the extended conjugated pi system of the protoberberine ring. So, a key factor here is methylene dioxide group, which is OCH2O, which acts as an auxochrome. So, by attached to the aromatic system, this auxochrome further extends to the conjugation, that allowing for absorption at this longer visible wavelength. Besides the standard pi to pi star electron transition, this peak also involves intramolecular charge transfer, which is ICT. So, the process where electron density moves from an electron donating group to an electron accepting group within the same molecule. So, this movement of charge within the molecule is a key reason for the absorption observed in this region. Connection to observed color, this absorption at 425 nm, which falls in the violet range, is directly responsible for the yellow color of berberine. So, as shown on this color wheel, when the molecule absorbs light in the violet region, the complementary color were observed is yellow. So, these transitions are governed by the principle that a longer wavelength signifies a reduced energy gap, as energy and wavelength are inversely proportional. So, that's all from
Hello and hi everyone. On this slide, I'm gonna explain to you guys about fluorescence spectrum. This slide shows the fluorescence spectrum of berberine. Fluorescence occurs when a molecule absorbs light and then re-emits light at a longer wavelength. In this study, berberine was excited using light with a wavelength of 421 nanometer, as you can see in figure 1. This is known as the excitation wavelength or lambda EX. After absorbing the energy, berberine emitted light at a longer wavelength. This emitted light is shown in the graph figure 1 as the fluorescence emission spectrum. The graph contains 3 curves because the researcher dissolved berberine in 3 different solvents: water, acetonitrile, and ethyl acetate. Although the solvent changes, the compound being studied remains berberine. In the spectrum, the dashed line represents berberine in water, the solid line represents berberine in acetonitrile, and the dotted line represents berberine in ethyl acetate. The emission maximum was observed at 555 nanometer for water, 537 nanometer for acetonitrile, and 520 nanometer for ethyl acetate. In figure 2, we can see the difference between the excitation wavelength and emission wavelength is called the Stokes shift. For berberine in water, the Stokes shift is 134 nanometer. This happens because some energy is lost through molecular vibration before light is emitted, causing the emitted light to have lower energy and a longer wavelength. The results also show that solvent polarity influences the fluorescent properties of berberine. Water, which is the most polar solvent among the 3, produces the largest redshift in the emission wavelength, while the less polar solvent, ethyl acetate, show the shortest emission wavelength.
Overall, the fluorescence spectrum confirms that berberine is a naturally fluorescent compound due to its conjugated aromatic structure.